how the other meetings you do go, but it would be nice to get that. So you're getting streamed, by the way. And what do they need to know to do that?
You just go to our Facebook page and it should be on there.
And we're
Oh, it's Nexus Energy Center.
Facebook.com/Nexus Energy
Center.
Center.
Mm-hmm.
Okay. I'll do mine when I sit down.
And even going
yeah.
back and doing it later when we're not live is still helpful.
Yeah.
Right. Uh-huh.
Mm-hmm.
Yeah. If you go to their video area, the other meeting they streamed is there. Energy Huntsville meetings are there. The trip they took to Raccoon Mountain is on there,
Yeah.
and all those other things. So there's a lot of good videos. I'd recommend that you go there.
Mm-hmm.
Yeah. And we keep this really informal, so I have to admit I don't even have your bio. Professor in biology, molecular biology.
Yeah, technically I'm trained in molecular biology, but over the years I've kind of woken up. Right? you can't really do stuff in a lab without getting out into the environment to understand reality. Right? So that's kind of where I'm at right now.
And we asked him very vaguely to come talk to us. So he is very vaguely getting introduced. There you go. How's that?
Sounds like a good day.
We'll ask you to speak a little loud if you can.
Yeah.
Just
Okay.
so,
I'll try to talk loud. If I start to peter out, just remind me. So yeah.
We can move the podium out here, and then you could like stand.
You're kind of far away. We can try that. I want to block the screen though. How's that? People still see? And yeah, so I'm over in the biology department, technically trained in cellular and molecular. Okay. And that kind of led to an interesting project where I started studying in the lab how plants and microbes interact, right? Mostly soil microbes. So I started out with fungi, and then working with Argonne National Labs and Brookhaven National Labs, started introducing different types of bacteria and things like that. And then the system started to get really complicated just with those three parts, right? But in reality, when you're outside, you have a bunch of different things going on in the soil. So that's really what I'm going to talk to you about. But I thought I'd start somewhere a little different. And I just wanted to ask the question, who knows what permaculture is?
Yeah.
So how would you define permaculture?
You're using mostly perennial plants and provide like a sustainable food system. Really, that's kind of how I view it. You're just using what's naturally there to create almost a constant food system.
I'd say it's just putting the organic material back into the soil and the ground to keep the nutrients going.
I would say those are both subsets of permaculture. So permaculture is interesting in my mind, not because I'm a hippie. I don't know if you know, like permaculture originally kind of got taken up by the hippies, and hippies are not very scientific or very meticulous necessarily. They're often very great people, right? They do awesome things, but they're not really that scientific-minded intensity that you need to actually make scientific discoveries, right? But there is a science behind permaculture that I find extremely interesting because it makes use of natural observations to actually do stuff that works. Right? So, well, here's a definition from someone that you're going to hear from soon. So you guys recognize that name, Alan Booker? So Alan came up with this definition. I think it's one of the best that I've seen, where permaculture is a comprehensive design science. Comprehensive being the whole picture, right? Based on observations in natural systems. That's really what's important. You're basically looking at nature. You go and you find the stuff that's working in nature, then you ask the question, okay, how's nature doing that, and can we do it? So you use those natural systems for creating regenerative systems. I'll get to that in a second. That support human communities sustainably over the time scale of centuries. Does that sound good? Regenerative systems that improve over centuries. So this word right here is kind of important. Regenerative, because I know that right now people view sustainability as a very positive thing, right? Sounds good. But the world has a lot of problems right now. And in the minds of a lot of permaculturists or permaculture design engineers, sustainability is actually a bad word. So, because why would you sustain something that's already kind of sick? Right? So they choose the word regenerative because it sounds good. And Alan even uses an interesting example where, how would you feel if you, is anybody married here? How would you feel if you had to describe your marriage as sustainable? Doesn't have the same connotation, right? Like, as rejuvenating or regenerative, right? Like, that's kind of where we're coming from. So the overall objective ties into this idea of sustainability, where you're taking a system that requires a lot of work and doesn't really produce a heck of a lot into a system that requires less work because you're letting nature do its job, and you end up with a lot more productivity. So in permaculture, there's these things where you do like sector analysis and whatnot. I know you have a tiny house project, right? Which I think is awesome. But in reality, if you were going to do a tiny house on a piece of property somewhere, the perspective is actually flipped in permaculture. What you do is you design the entire environment before you even really consider building a house, right? Or your dwelling location. I'll get to that in a second. So this is part of how a permaculturist would look at the overall environment, right? And one way is that, so this is one that I did for property out in Gurley, and the overall idea was that there were some mountains off in this direction and whatnot. Those things have an impact on the overall environment right here, even though you can't even see where the house is. It's kind of like right there. But there are these other sectors that you have to consider, like in the summer, the sun sweeps across the landscape a certain way, and that sweep is smaller in the winter, right? So if you're going to have a house down there, you can actually design your house to take optimal advantage of that sun's energy for heating, in some cases for cooling, if you have the right types of structures like cooling towers and things like that. So where does the water enter? That's like a really big one. It's kind of important. Prevailing winds, that's a big one too, because if you have a structure on this piece of property and you have this cold prevailing wind coming from the northwest, right? You might want to plant some trees on that side of your house, right, to kind of buffer that wind. Okay? And then there's other things like, where do you have like a nice view going on? How do you get into the property? Right? Where do the animals come from? Because if you're actually trying to grow something and make a profit, right? Then if you have these animals coming in and they're eating it all, that's a problem, right? So you can often do something to help curb that flow of animals. So sector analysis is something you hear a lot about. You guys are welcome to just, if you have any questions, just jump in since we're keeping it informal. Another thing in permaculture though is to reduce your work effort. They often talk about zones. Okay, you heard that with permaculture stuff? People that do know about it, zone analysis really. So the overall idea is that your dwelling might be here. That's where you spend the most amount of your time. Okay? You live there, you sleep there, you cook there, and stuff like that. So right around the house, you put a lot of time and energy into that space. You don't necessarily want to have to, if you have something really important near your house, like your little kitchen garden or something like that, you don't want to walk a half mile to your kitchen garden to get your cherry tomatoes for the salad that you just put together. Right? So you put it really close to the house. That's the overall idea. That reduces the workload. So then there's things like places where you might have that kitchen garden close to the house, places where you might have a more intensively managed area like a production garden. Other places where you could have things out here like some forested area. Okay, things that you don't need to manage as much. You put further away from your dwelling because it takes energy to get there and back. Right. Another thing with this is topography too. Like if you're growing stuff and whatnot, and you're going to be producing something, you don't want to move it uphill. Right? Like even if you're using machinery, right, it takes more energy and gas to go uphill than it does to go downhill. So if you can position things properly on your property, then you'll be in good shape. Now this is kind of an important zone out here, zone 5, where you need to have some natural area, right? Because it's the natural environment that actually supports the efforts that are going in closer to the dwelling. Okay? So there's a variety of famous permaculture-oriented people that were not just hippies, but like really sophisticated, scientifically oriented hippies. One of them was Yeoman, right? And he came up with this whole idea that if you're trying to engineer like an entire environment, right? People will often go ah, right? Like you don't even know where to start. So he just put things in order of what he calls permanence. Okay? So for things like climate and landscape, right? The landform around you, there's not really much you can do. Right? You can't do anything about climate really, right? So maybe over centuries or something, chopping down forests and whatnot, the climate will change, right? We do have climate change happening, but not much that you can do about it right now. And the same thing with landform, right? Mountains and stuff like that, difficult to change. You can change things on a smaller scale, but not much so on a big scale, right? The water supply is actually really important. Most of the properties that you can get where you're going to put a house or something like that, the whole objective of that piece of land is to get rid of the water as fast as possible, right? Which from a productivity point of view is a really bad idea. Really what you should be doing is trying to grab that water and store it in a proper place, right, where it's not going to like flood your house and stuff like that. But then keep it on your property as long as possible so that you can use it in order to, say, grow crops or do your aquaponics or aquaculture, or so drinking water even. So. Oh, speaking of which, somebody mentioned about for a tiny house drinking water system. I have a Berkey water filter. And it's pretty awesome. Like if you haven't heard of it, you should look it up. Berkey, right? It's just a stainless steel container that has 2 levels to it. It's got a big carbon filter in the top, and you can get other filters for the bottom for arsenic and lead and things like that, right? And all you do is put your water in the top, and it will percolate through at a pretty high volume rate. The nice thing about it is that, yeah, it's a filter, but it is gravity fed, so you really don't need power. If power goes out, you can still have your filtered water. And it can take the most scummy water that you can imagine.
Or rainwater.
Yeah, rainwater.
Like our tiny home, we have a gutter system that goes to rain barrels. That rain barrel could go to a Berkey.
Yep. And then the Berkey would do a great job cleaning up any other residual bird poop or something like that, right? Plus there's first flush filters and things that you can get for the roof systems where it'll basically rinse the roof off and put that water somewhere else before it starts to collect your rainwater for drinking or bathing or whatever. So,
There are a lot of products on the market now that can do that for cheaper as well.
yep. Yeah, it's a really simple technology that works great. But yeah, the Berkey filter, it turns out that for really pure water, I think it's about 7 cents a gallon. If you really calculate it out, because these filters will last for like 10 years. It's pretty impressive. You might have to back flush them. So water's a big deal, and that's why I have this little picture here. So it's that same piece of property, but what I did was just using the topography of the land, I just figured out where all the water was going, so that on the piece of property, you can start to figure out, okay, maybe we need to have a pond here. This would be the easiest place to have a pond. We can capture the water there, high up on the landscape, and use that to water things a little bit further down.
How did you spell that water filter?
Berkey, B-E-R-K-E-Y. Berkey. K-E-Y. So,
B-E-R-K-E-Y.
I think so. You should just be able to type it in there. Like I guess the Queen of England has one. That's got to be good.
Yeah.
It's probably because of her son. Because Prince Charles is pretty big on
Really big on
sustainability too, right? You don't know already. He's got some cool ideas. Anyway, these orders of permanence. Water is really important. In fact, they often say that if you can fix the water on your property, even before you build your house, then you've already solved about 70% of the problems that you'll have down the line. It's that important. Yeah. Then there's an idea like you have to be able to access the land, especially while building. There's trees that you might want to have planted because they take a while to grow, right? So like on that northwest side where the wind was blowing in. Then finally you get to a structure. So the overall point of this is that, when you consider, yes, get experience building a tiny house and whatnot, but in the future, if you actually get some land or something, you might want to put some effort into flipping your perspective. Don't just jump on there and build a house. That's what everybody does. And then eventually they try to figure out, okay, this part of my property is not really doing much for me, so let's try to re-engineer it, but then the house is already in the wrong spot. So if you flip your perspective and try to design the overall ecosystem first, then often your house ends up in a place that's much better suited, right? And requires less energy, and less energy usually equates to better sustainability. Okay. So what I'm really interested in is way down here, at the very bottom. One of the easiest things to manipulate on your property, like especially if you have a garden or you want to do some kind of larger food type production. So soil. What is soil? Well, there's a few definitions out there, but the traditional one that you might hear from people is that it's material that nourishes and supports plant growth, right? Essentially, it's coming from rock, right? I don't know if you really understand that or not, but our soil comes from degraded rock. Okay? And what's the nice thing about that rock is that it has most of the nutrients that the plant actually needs. So, from a geological perspective, this is much closer to the current agricultural perspective on soil. I'll tell you that in a second. But from the geological perspective, it's the loose surface of the earth that's distinguished from solid rock. So, does anybody know how modern agriculture kind of views soil?
Just add more and more fertilizers and
Yeah.
more and more.
That's the chemical part of it. That's what you have to add to this stuff that is so.
Just rotate your crops and your soil will be fine.
To
Yeah, that's
loosen it up.
part of it.
They mine it and exploit it.
Yep, that's true too. So from my perspective, the way that modern industry is thinking of soil is that it is a substance on the Earth's surface that is designed to prevent plants from falling over. And that's it. I don't think. It's mostly because of the emphasis on chemical fertilizers, right? Because we have taken, as human beings, we've taken the responsibility of feeding our plants. In nature, does that really happen? Say you're walking through a really healthy forest or something like that. Do you see any bags of fertilizer out there, or any plants in need of like some human going, you have a molybdenum deficiency, I will go get it for you. So the point is that when we take on the responsibility of the feeding of the plants, we take on a lot of responsibility, because in nature the whole biosphere is really designed to cycle these nutrients very efficiently. And if we pay attention and try to figure out how nature is doing it, then we can save a lot of time and energy. So this thing down here is just as an example. So the components of soil, most of the time people think, okay, there's some mineral material there, and then there's some organic material. But the vast majority of people really forget about the fact that soil has to have water in it, right? And soil has to have air in it, right? And part of this organic material, what else is needed in there? To call it soil. There's a difference between dirt and soil. So to call it soil, what else do you need?
Like some organisms?
Yeah, you need life. It's got to be alive, because it's especially the microorganisms in that soil that will mine the nutrients from the rock, the little particles of rock, and they will deliver it to the plants. Okay? And that's like that's one major way that plants get their nutrients. So dirt. It's a correct term too, but it's really just comes down to sand, silt, and clay. So this is a little. I don't know if we can turn these lights on. Is there a switch for that?
No.
So this big kind of faint glow back here is a piece of sand, okay? And sand ranges from really big to really small. So it tends to be the biggest. Silt is smaller, and then clay are these ridiculously small little flat pieces of soil, I guess you could say, well, dirt, right? And they have a pretty strong negative charge on them, which has both positive sides and negative sides. I won't go into that, but if you have sand, silt, and clay, you could say you have dirt. If you start to add organic material and life in there, then you can start talking about soil. Okay? And having that water and the air in there is also really important, because plant roots need water, right? Or just suck it up and send it to the tops of the plant, right? All the biological enzymatic reactions and whatnot are in aqueous solutions, so they need to have water. And at the same time, plant roots also need to respire. What's necessary for respiration? If you're breathing, what are you doing? Yeah, you're taking Okay, taking in oxygen, releasing carbon dioxide. Well, plant roots do the exact same thing. It's not all photosynthesis, right? Plant cells respire as well as do photosynthesis if they're green. Okay. What I'm talking about here is time is needed for good soil. There is most young soils, and I'll ask you what that is in a second, so think about it. Most young soils are low in nitrogen, right? And they tend to be high in phosphorus, because phosphorus doesn't really leach as much as nitrogen does. Nitrogen in the form of nitrate will, like when you add those chemical fertilizers and it rains the first time, you typically lose about 50% of everything you just put on the ground, right? And it just goes down into the water, in the soil, it goes downstream, usually to some stream, right? And then there's like an algal bloom, right, which sucks all the oxygen out of the water and kills fish and stuff like that, right? So you kind of know that scenario, right? Mature soils, on the other hand, are generally very productive. So my question to you is, what is a young soil? And how old is it?
Put it in last weekend.
Would you consider that like glacial leavings or something?
So a glacier could go by and scrape the surface, like the topsoil off. I'll talk about that in a second.
Or a lava flow or something.
Lava flow, or
Like leaves falling and like just starting of soil, those type of decomposition.
at least starting would be a little bit further down the successional line. What about where they're building the new dorm over here, wherever we are, but over there? Have you seen the bulldozers going along? Well, guess what? They're making young soil, right? So it's this disrupted soil that is low in nitrogen, high in phosphorus, and there's not much stuff growing there. Okay. How long do you think it takes before a young soil actually starts to mature, like in nature?
Oh wow, they have to have decomposition.
Yeah. So how many years do you think?
Several. Maybe 4 years, 4 or 5 years.
Typically, it's in excess of 100 years. If left to its own accord. But what I'm going to tell you is that there are ways to get it to be more mature much more quickly. Okay? So, and old soils, as you use them over and over and over and over again, eventually the plants build up a bunch of nitrogen, but the phosphorus, because you've been moving things off of the land, like cutting plants, moving them, potassium will go down. And your soil structure generally starts to kind of fall apart too. So you can also do things to kind of have old soils back up to mature soils. Hey, enough about that. So if we look at like a cross section through the soil here, you can talk about soil horizons. Usually there's an organic layer at the top, and then there's topsoil underneath it where you have this organic material kind of degrading. Lots of life, if it's a healthy soil, right, that are helping with the decomposition here. Then you have the subsoil where the roots really kind of penetrate. And there's kind of a layer at the bottom of the subsoil here that if there is leaching occurring, that's where a lot of nutrients will build up. And right below that is what's called the parent material. And that really is kind of weathered rock, right? And a lot of times as the plants are growing and stuff like that, they'll start to break some of this material up and whatnot with their roots, because the roots get in there and then they spread things apart. Okay? If there's freezing and thawing, there's all kinds of things that will help produce smaller pieces of rock. When you have those tiny pieces of rock, then you can have microbes and whatnot that can get in there on the larger surface area relative to volume, right? And then they start to nibble away. And what's interesting about them is that, yes, they'll take in nutrients and they will grow their own bodies, but microbes will life cycle a lot faster than, say, plants and animals and things like that, right? They go through many cycles of living and dying. When they die, what do you think happens? They release their nutrients, right? But more importantly, if they interact with the plant roots, like down in this area, they can also deliver those nutrients to the plants directly. And what's really interesting is how plants communicate that. Plants actually talk to the soil. They actually secrete stuff in the soil to feed the microbes. Okay? And then the microbes in exchange will feed the plant other types of minerals, which I'll get to in a second. Okay? So this type of communication is actually really, really sophisticated, and people are just starting to figure it out. Because something like a tree, so I'll be a tree for a second. If there's a leaf up here in this tree, and this leaf determines, right, that it needs some more magnesium to make some chlorophyll, it will actually send a signal down out the root and into the ground and say, magnesium needed, and some bacteria down here will go, I can get that, I got it right here. So I'll give it to you in exchange for some sugar. Okay? So the plant makes some sugar, sends that down, right? right? And the bacteria gives back the magnesium, so the plant sucks it up. And it really is like this opposite. This side of the tree is connected to this root over here. So they cross over at a certain point. So it's really pretty complicated communication that goes on in the soil when you have living organisms in there. So these are just the nutrients that plants need, just to give you an idea. Nearly all this stuff is contained directly in rock. Right? It's all there. So there are some non-mineral nutrients, this carbon, hydrogen, oxygen that is available to the plant, and then even nitrogen, which is also in the atmosphere, right? There are certain processes where nitrogen is taken up by bacteria, converted into nitrates for the plants, and that's all fine and dandy, right? The carbon and the oxygen, where does that come from for plants?
Here.
The air, yeah, the carbon dioxide, right? So carbon dioxide is taken up, and it's used to do what? To help with photosynthesis. And you make sugars. And those sugars eventually start to make cellulose, which is most of the plant's body. So one really cool thing to think about is if you go look at any tree, right? If that tree is made of cellulose, which came from carbon dioxide, then literally that tree is precipitating out of thin air. It's really just coming together that way. So it's the, everybody talks about the importance of the climate change and what's going on with the CO2 levels in the atmosphere and everything. But what I'm going to do is I'm going to make a case that the soil is also a very important resource. So I can actually back up here and ask you a simple question. When we're talking about the atmosphere and the CO2 concern, right? Like how thick are we talking? How thick is this atmosphere that we're talking about?
A mile or something.
Like the overall, let's say all the way up to where like the ozone layer is and stuff like that.
Thousand.
Any idea?
100 plus miles.
So if you go way out there, yeah, you could do
I mean, the very tip of about 300 miles up, where they start to say, "Oh, this is space."
Yeah, well, at 300 miles up, you actually have things orbiting the planet too. So this place where there is carbon dioxide and cycling between oxygen, carbon dioxide, and these other chemicals are up there, around 20 miles. Like it's something that you could probably walk in a day if you walked straight up. So let's say around here, how far do you think it is from the surface where the grass is growing down to the parent material?
It says 30 inches.
That sounds ridiculous, but that's why I say around here. You ever dug a hole in your yard or something? Like, where do you run into clay?
Like 6 inches, yeah.
Yeah, maybe 4.
Yeah.
About 4 inches, right? So literally, you can have that in the palm of your hand, right? So, and this resource is a very slowly renewing resource that people don't really care about very much, and they really should, because for every ton of soil, it's just one of the latest statistics. For every ton of soil, for every ton of plant material that we grow for food and whatnot, we actually lose about 6 tons of soil. And that's the current rate. I mean, it used to be a lot worse, right? We're hearing stories about the Dust Bowl and stuff like that. But mostly that's from erosion going downstream and out into the ocean. And then we're not doing a good job replenishing that. So what I've been interested in is, how do these nutrients get cycled from essentially rock to the plants? So just to give you guys a perspective on that, when you're talking about a plant, right, and you look at a root, the nutrients are taken in by root hairs, right, and then they will go either through or around the cells of the root to a little layer that's called the pericycle, right, and that will decide whether or not the plant should let it in or not. On the inside of the root, there's actually vascular material, right? Xylem and phloem, you've heard about that. So the xylem will suck those up along with water, the soluble nutrients, and the phloem will allow the plant to produce sugars and whatnot and pass them down to the root to feed non-green material. Okay. That's kind of what we're talking about. What's also interesting is that, so here's that same picture right here. Here's a root here. So I'm putting this back up here to remind you about the water in the air. So water and air are really important, because as the root hair penetrates these soil particles, right, there has to be some space in here. And there has to be water there because plants take up nutrients in these two ways. Right? One way is through soluble chemicals, right? Which is what our modern agricultural industry is totally focused on. Do you know why they're focused on the chemical side of this thing?
Control.
Control. Who's they?
So petroleum industry.
Really, yeah. So there's only a handful of chemical companies that literally control all of our agriculture. In fact, it's the chemical companies that own the seed companies too. So,
And a lot of our medicines, modern.
medicines, yep. So I don't think it was intentional, but we developed a system that is so chemically oriented that we have now a system that we can't get away from chemicals, right? At least at a large scale, because we haven't done a good job looking at the other way that nature actually deals with passing nutrients around, and that's through biological methods. So in nature, what happens is that you get bacteria and fungi all through here, which significantly increase the surface area of the root and actually control what nutrients can be taken out of the soil particles and passed to the plant. Right? So there are literally for every root, for every like square centimeter of soil, and that changes from place to place. Like you go from 1 square centimeter to the next square centimeter, you might have completely different organisms in that. And so it's extraordinarily complicated. Right? So there's hundreds of different fungi, thousands of different bacteria that are existing inside of, or at least attached to the roots, and they're really controlling how the plant is taking up nutrients in nice, healthy, natural systems. Okay. You guys know how big? Let's say it's a tree. We'll look at this tree. How much of the tree is above ground and how much is below ground?
That's 50-50. Half and half.
Depends on where you are, right? So if we start down in the rainforests, right, the ratio is really quite different. Usually about 90% of the tree is above ground and only 10% is below ground. And that soil is really, really thin. And that's one reason that if you lop the trees down, like it just all goes to shit, basically. You know, so it's really hard to like get it back. If you head up through the temperate zone here, around here, it's usually about 60% below ground, 40%. As you go a little further north, you get the ratio underground increasing up to a point until you end up in the Arctic, where usually plants are they have pretty big root systems, but the plant overall is very tiny just because of the extreme climate, right? And then there's just a little bit above ground, just enough to kind of get the sun's energy.
But the root systems are still big, even with permafrost?
Yeah, they are. But the plant is just so small that,
Yeah.
see what I'm saying? Like, if you were to pull the plant up, you would see a more root system. All right. And as far as climate change is going on, yeah, people are interested in toxic rain and what the CO2 is doing for the greenhouse effect and all that. But people are also concerned that it will very likely change the way that the nutrients are moving in the soil to the plants, mostly because there's fungi and bacteria and protozoans and nematodes and microarthropods and insects and worms and all this stuff in the soil that's also being impacted by these changes. So I kind of already alluded to this, the current chemical fertilizers. So remember this picture here? What a plant actually needs, right there. Right? It's about 16 chemicals. And when you buy a bag of fertilizer, how many of those are in it? There's 3, right? NPK, right? So it's just these. Especially when it comes to nitrogen, that tends to be the one that the plants use the most. Okay? So there's some problems with the current chemical industry, right? Not only are they very fixated on just the soluble chemicals that the plant can take up, but they're also really fixated on just these 3 chemicals, right? And they neglect the other ones for the most part. Okay? So when you're dealing with like modern farming, you get some problems occurring because the artificial fertilizers do a variety of things. Right? One, the fertilizers themselves are washed away from the soil, right? And then they go and they pollute rivers and lakes. I think that was pretty obvious. Right? They also artificial fertilizers will reduce the organic matter. And when you reduce organic matter, what you start to do is you start to break down the soil structure. I think I have that on a list here somewhere. Right? And when you break down soil structure, it can't hold together as well. Right? And in addition, the organic matter also typically supports life. Right? So if you have microbes growing in there, let's think about a fungal mat going into the soil. It'll actually hold that soil together. So if you add only chemical fertilizers, the natural way that plants and microbes actually interact is sort of broken because the plant's sort of being force-fed chemicals. Right? So they don't necessarily set up interactions with the soil microbes anymore. So the soil microbes suffer, they start to reduce, and that basically breaks down the soil structure. You get reduction in aeration occurring. This whole process can be considered addictive, right? Can be considered addictive, mostly because once you start to add chemical fertilizers in there, then next year it's harder to grow any biological sources of those. So then you have to add more chemical fertilizers, which just makes it worse. And then these soils get essentially addicted to the situation. When it comes to nitrogen, does anybody know the process that they use to make nitrogen?
Especially pull it from the air.
Yeah, they can pull it from the air. And the name of that process is the Haber-Bosch process, right? It was actually created in World War II to help make bombs because you essentially get ammonia out of it. Right? So ammonia is just a nitrogen with hydrogens on it. So my question is, where do those hydrogens come from? Right? It sounds like a great process. Just suck it out of the air and you get all the nitrogen you could possibly need. But where do the hydrogens come from?
Water, I guess?
Nope. It takes too much energy to break water and use the hydrogen. Actually, fossil fuels. They use natural gas for the most part. So you're burning fossil fuels to make your nitrogen. And that's where you use a lot of fossil fuels to make the fertilizers that are derived from that. Yeah?
Could you explain maybe a little better about how the organic matter is reduced? Like, what's kind of the process behind that?
Well, organic matter needs like kind of constant addition, okay? Because over time it starts to break down. Right? Those little particles will eventually run out of nutrients and whatnot, and then they become a part of the soil that can be eroded, right? So not only does the nutrient level go down, but the little particles will eventually kind of wash away with raining. So over time, it gets reduced.
Because
You're not continually adding to it.
when you're adding artificial chemicals, you're not replenishing the organic matter.
Right. And when I'm talking organic matter, I'm not just talking plant material, I'm talking the biological material that is in there. So the bacteria and fungi and everything else that's in all the trophic levels.
The microbes and all those organisms kind of help stabilize the soil and bring more nutrients into the soil as well.
Yeah, and they're part of the overall food web. Right?
Yeah.
If you have a break in that food web, there's a break in the overall flow of energy.
Right. So you know you have good soil and you dig it up and you got a bunch of worms wriggling around.
Yep. Worms and small insects, things that you can see. And a lot of the compounds in these artificial fertilizers will actually build up in animal systems over time, including us. So one of the things that we do, I have all kinds of stuff to talk to you guys about. One of the things that we do is we look at small systems in the laboratory to try to make some sense out of the complexity that's out there. So we set up these little boxes and we can add like certain microbes. We don't actually put a mushroom in there, but it's just like and so we change the conditions and whatnot, and then we look at what happens. So one of the things that we noticed early on is that this red bar has fungi that are associated with the roots. They make a symbiotic relationship, right? And they do just fine. They actually increase the biomass of the plants that we're using by like 81%. That's pretty significant. There's a caveat though. They only do it. WPM is a media that has like plenty of nitrogen in it, so the nitrogen's already there. When you start to reduce that nitrogen, then that effect goes away. Right? So what does that mean? That means that without the right nutrients, then the microbes don't do their job. Right? So you have to. So there's like this kind of catch-22, right? if you need soil that has nutrients in it to get these biology type organisms to come in to help make more biomass, right? And then but if you don't have the microbes there, then the nitrogen goes down anyway. So you really start to break that system. What does this really look like? It looks like something like this. Where we have these little boxes where we can grow like little trees, and then you can add fungi to it or bacteria. You can kind of see them growing here a little bit, right? And then we grow a whole bunch of them. We do all kinds of crazy things. I don't even know if you guys know what transcriptomics is, proteomics, genomics, metabolomics, right? Like, so what we're doing is we're looking at the expression of all these genes and what they're doing, not just in the plant but also in the microbes, right? And then we try to figure out how it's all connected, right? So you get these crazy things that are trying to show connections, and you try to figure out how the systems are interacting and stuff like that. And that's all I really need to say about this, but it just generates these networks of information where you're really just trying to figure out what the plants and bacteria and fungi, right? So here's the bacteria, plant, the fungi, right? And it leads to a phenotype. And the phenotype that we're really interested in is biomass. Why? Because that's the thing that we use, right? We can use it for fuel, not just for us, but like our cars and things like that. And there's a variety of things that we do, but one cool aspect of it is with Brookhaven National Labs, this is a piece of equipment, just to let you know. It's huge. Can you see a car here? Little bitty car. This is called a synchrotron, right? And really what it does is it makes light, okay? And so there's a beam in this facility that is an infrared beam, and we can use that beam to look at little plant roots, right? Microscopically, even all the way up to the root hairs, right? And so what we get out of that is, here's the root here, right? And this coloration here is a fungal mat that's attached to the root. Okay. So what the fungus is doing here, and you can see from here, every single pixel on this picture actually contains the entire infrared spectrum. So what you can do with that is you can tune your picture to a certain type of compound, right? So what this picture is tuned to is nitrate. Okay. So what the fungus is doing here is it's grabbing nitrate from out here and it's pulling it towards the plant, and you can actually visualize that. You can see it. It's pretty cool. On the other hand, this one here, this is even more interesting. The plant is actually secreting something into the media. This one is sucrose. So the plant is releasing sugar into the media in order to help feed the microbes out there. So you can see the result up here. So it's some of the cool stuff that we do, playing around with small scale. Bottom line though is it really doesn't have much to do with reality because in reality it's a lot more complicated. So I want to ask you about this. You guys have seen this kind of stuff before, right? With succession? Right? Familiar, right? Basically pioneer plants. What's another name for pioneer plants?
Annuals? Was that what the annual plants are? Is that what you mean?
Well, a lot of them are annuals, yeah, but there is another name, a very common name for pioneer plants.
Moss.
Weeds, yeah.
Weeds. Usually they're the things that you don't want, right? Like, especially if they're pioneer plants in your lawn, right? So the pioneer plants give way to perennial plants, and then eventually shrubs, and a little bit bigger trees, and finally climax forests.
My weeds are perennial.
And I think these are dandelions here, right? But dandelions are awesome plants. Like, they're totally edible. Did you know even the latex in those things is edible? It always scared me, but yeah, apparently it's all very medicinal and good for you and stuff like that. So we really should be cultivating dandelions. Some European countries do that. But what actually controls this? Do you have any idea? Erosion.
What actually controls what?
What controls this succession? It's the succession, right? So why does it success?
Soil depth.
Soil depth, yeah, that's part of it. So what makes soil?
Microbiology?
The microbiology. You get the idea, right? Okay. So when you're first starting with like young soil is really dominated by bacteria. And then when you're talking about a final climax forest and whatnot, especially like conifers, it's very fungally dominated.
Okay.
So what you can do, which is really kind of interesting, is that if we know that we have our vegetable crops here, you can tune the sort of concentrations of bacteria versus fungi to to a level where you can inhibit pioneer plants, in other words, weeds, and you can promote the growth of plants that you actually want. How do you do that? Well, that's what I'm working on. So what I've been doing here, I have a lot of pictures now, so I'm going to try to time it right for you guys. What I've been doing here at the community garden, this is Mike Marshall. He helped a lot with this, and behind us is the community garden. One of the things that we did was we started a project called the Sustainable Fertilizer Initiative. Okay. That sounded good, right? It had the word sustainable in it. So it worked. So we first built a garden, right? And there's a little shed back here, which is going to be important in a little bit. Right? Part of the garden, by the way, this is a couple extra little notes here. Part of the garden, we have our annual plant sale. Has anybody ever done plant sale? We usually have it right when the plant sale at the Botanical Gardens happens too, except we sell vegetable plants. Okay? So it's like April 15th, right around there. And it's been very popular, and it's actually that's the way that I figured out how to fund the garden. And that's the only income that we really get. So we also have had, this is Alan Booker, by the way. So we've had workshops on soil life, soil fertility. There's actually one coming up in April. If you want to attend, I'm sure Alan will say something about it because he's coming in March, right? So the Sustainable Fertilizer Initiative, really its function is to make something called compost tea. Does anybody know what compost tea is?
Yeah.
Yeah. So you've heard of that one, right?
Mm-hmm.
Yeah.
So it's really just a way of culturing up a whole lot of really good microorganisms. Okay? Then you can add those to your plants. Yeah, it has some nutrients in it too, but it's really the biology that is so important. So in order to have good compost tea, you actually have to have good compost. So we do some classes with compost tea and whatnot. That compost then goes into this facility back here. It's still down there at the south end of campus. You can look at it. So what it is one, it's a little classroom because we built the roof up here because it was really annoying to try to teach while we're getting beaten down by the sun or suddenly it rains, right, and stuff like that. So we can duck under here. But more importantly, this acts as a rainwater collection device that goes into this 1,300-gallon tank. That provides us with something really important. It's chlorine-free water. You'd be surprised at how bad chlorine is for microorganisms, right? So we end up with good water that can go inside of a facility inside of here. Up here, what's that?
Green roof?
Yep, solar panels. So we used, let me just say that this facility will make compost tea using only rainwater, compost, and solar energy. So I think it's pretty cool. This is the brewer that we use. It's a dirt simple brewer, and inside of here, it blows air up in there because aeration with compost tea is extremely important. If you don't know, a lot of pathogenic microorganisms are anaerobes. Okay? So if you have compost tea that goes anaerobic, some people like to use that, and sometimes they're lucky, but inevitably, eventually, you'll probably get some sort of pathogen for your plants. So it's really important to have. There's a really big blower down here. It's like a 650-watt blower, so you can see how much good energy we're getting out of this solar power system. But it'll blow air pretty intensely up through there and keep everything nicely aerated. Okay. Then we can take it using like a truck and trailer that I bought. And there's a little Kubota with a sprayer on the back, and we can treat things like our community garden, right? So we have all these little plots and whatnot, and what I did was for research purposes, we planted the same types of plants in adjacent plots, and then we treated with compost tea, and here's something that we got. So this is one plot that has some early season growing type plants in it, right? And they get to a certain size, right? And if you look at a plot that's been treated with the compost tea, hopefully you can see that there is a considerable difference there, okay?
Same age?
Same age, they were planted at the same time, roughly the same numbers, not necessarily the same position, but roughly the same numbers. And this is just here because I was thinking about covering them, but then I did when I took pictures. Question?
And how does that compare to the nasty chemical fertilizer?
That's a very good question because out in Madison, I started making even bigger outdoor plots, okay? And this is just jute that we've planted like specific plants with. And we would care for those plants as they were coming up and whatnot, and monitor them over a season where we actually did treat with fertilizer. Right? That's one thing is the control. We didn't treat with anything, right? Then there's treated with fertilizer only. There's treated with compost tea only, and then there's treated with both compost tea and fertilizer. And you can kind of see some of the differences here. So these ones that are darker green are the ones that got the compost tea. Right?
Do they have any pesticides too, or is it just
No,
more fertilizer?
just that one treatment. It was actually 3 treatments over a season, and we've done this in the greenhouse too. And what we're doing right now with Hudson Alpha is we took soil samples and we extracted the DNA out of them, and so we're going to look at what organisms are actually there, and hopefully look at which ones moved up into the.
Are you going to look at the root again too, and the?
Yeah, so we did. So one really cool thing that happens with compost tea. Hopefully you don't mind if I go over a little bit. Right? You're familiar with compaction?
Yeah.
So, compaction, soil compaction. This is a big problem on farms and things like that because you have the equipment driving up and down and whatnot, or even gravity over time, just kind of making the soil particles really compacted. When the soil gets really compacted, the roots can't penetrate that anymore. Go dig a hole out here. I guarantee you'll understand what compaction is about 4 to 6 inches down. Okay? It'll get real hard. Well, plants have a hard time getting through that. What's really interesting is that the compost tea, when you treat it, in these types of plots here, there's a device called a penetrometer where you can measure how deep the roots can really go for the plants, and the compaction is reduced by half. So what that means is that those microorganisms can get down in the soil and loosen those soil particles enough where the roots can penetrate twice as far. And what's that going to do for the plant? Well, it'll make it look like those garden plots that I had up here, right? Like this guy. Right? So because there's more water, more access to nutrients and everything, so they just grow better. So that's one of the big differences that we saw with the compost tea. Okay. So some of the things that I have here is that you have to have the right combination of microbes associated with the plant, right? That actually helps the plant grow because it delivers more nutrients, but it also helps the plant's immune system. When a plant is really healthy, they have less insect attack on them. Okay. So a lot of times when they have more nutrients, they can produce the compounds that will fend off the bugs. So that's another factor. In the future, I would say that there's probably going to be a new push to using our giant human brains to actually observe nature, start to figure out, okay, how does nature do it? Let's maybe do that too, right? Because I think that'll be a big part of the sustainable efforts. Okay? And then there's this weird statement down here, right? So a new hypothesis, this has to be all sciencey, right? So we hypothesize that the specific soil community composition, in other words, who's there, right, is probably less important than the emergent properties of those systems. What does that mean? What's even an emergent property?
Like what's
Makes
coming?
sense to me, I just can't define it.
What the new organisms are actually bringing to the soil.
Yeah. So when you have things come together, like elements of a system, a lot of times the effect that you see is something even bigger than what you would think would be caused by those two things. Okay. So a really good example is if you're driving down the expressway and you run into like a bunch of traffic, and it's real slow for a while, and then it just clears up, and you're like, well, what the heck was that? That was an emergent property of the fact that maybe as much as a half an hour ago, a deer jumped out in front of somebody's car, and they slammed on the brakes, and everybody started slowing down. So then this whole system like slowed down.
Mm-hmm.
So what we're saying here is that it might not matter exactly which organisms are there. What might matter is what they're doing, really. Okay. So this is important. This is like the last little bit here. So this is important because after the Industrial Revolution, we really had a situation where our population started to increase because of access to more materials, right? But at the same time, our energy started to go up, right? And what was the energy consumption, right? You can see that per person, it's kind of flattening out at this point. But this is associated with this paper down here, which is a really good paper if you get a chance to see it. What these scientists did was they kind of viewed the Earth as a giant battery. Okay? So here's the Earth. And what you can essentially do is using the sun, you can trickle charge the Earth. You can charge it up. So what is that device on the earth that can actually take the sun's energy and
Plant.
use it to put into into something that stores energy? Yeah, it's the biosphere, really. Right? It's the plants and the bacteria that are photosynthetic. Right? And over time, some of that actually became fossilized. Right? So we're tapping into that right now, and we're re-releasing that. So all that stored energy, they tried to figure out how much was there, how fast are people using it, how much is already gone, and what they concluded is that over the last 100 years, we have used about 40 to 50% of all the stored energy on the planet. So what that means is, if it's 50%, right? If we go another 100 years at the same rate, there's going to be some big problems. So we need to figure that out. So this is what I have here: is that if we really want to have a productive and healthy environment, then we should do everything we can to maintain the health and vitality of the soil. And a lot of that has to do with feeding the organisms that are there that help support all the plant life, which also helps to support us. Okay.
Thank you. I didn't mean to terminate the meeting, but I know some people really